In this video, we're going to look at the quantity of numbers that we can produce given a set number of digits in a bit number system, as well as the highest number, which for an unsigned system will be, there's a pretty tight relationship. So if we start by thinking of just if we have one place or one digit, how many numbers can we put in here? Well, that's going to depend on the base. Let's say we use a base 10 system. Those could be the numbers technically 0, 1, 2, etc., all the way up to 9. So this will give us 10 possible digits, but the highest one is going to be 9. If we extend this out to 2 digits, then we can have 0 to 9 here, and 0 to 9 here. Technically, 1, 2, 3, 4, 5, 6, 7, 8, 9 in here would have a leading 0. In this case, there's for each group of 10 here, there's a corresponding group of 10 here. So that's going to give us 100 possible numbers. And you can easily see this yourself if you just put in each position your highest possible symbol, base 10, would be 9. So we have from 1 to 99, but then we still have to consider the case where we had 0, 0. So there's 99 numbers there, and then 0 gives us 100 possible. So if we're looking to see what will adding additional digits give us, what capability will that give us, if we add another one on here, well, effectively what you're doing is you're multiplying the number of previous possible numbers by whatever our base is. So you should be able to see a pattern going from 1 to 2 to 3, where in this case we would have 1,000 possible digits, where 1,000 is just 100 times 10, because 10's our base. Great, so what? It's pretty clear with the decimal system, but a binary system gets to be a little bit trickier. So for binary, and let's just switch the color so it's easier to see, we can start off with a place. Blue is a little hard to see, let's go with red. So we'll start off with our one digit, and we can have our numbers 0 to 1. That's the only symbols that we're allowed to have in a binary system. Well, in that case, there's two possible numbers. If we have two positions, we could have 0 to 1 or 0 to 1, which will give us, we could have 0, 0, 0, 1, 1, 0, 1, 1. We're just trying to list every possible combination of the symbols that we could have for the given number of digits. And we're still following that same pattern where we're multiplying our previous possible quantity by whatever the base is. Binary system is base 2. If we have 3 positions, then we can have up to 8 numbers because we follow that same pattern. And we could list them out, but I'll run out of space quickly if I try to do that. If we want to get our biggest number, we could do that pattern that we used up here, where, assuming that these are unsigned numbers, we can just plug in whatever our highest symbol is. So pretty short choice here. So 1, 1, 1, and as we saw in the expansion video previously, that would just be 1 times 2 to the 0, 1, 2. That's counting for the place for the digits. Plus 1, that's this one, times 2 to the 1, plus 1 times 2 to the 0. 2 squared is 4. So 4 plus 2 plus 1 will give us 7. So notice that relationship here as well. The quantity of digits will be 1 more than the highest number. And we had that same relationship for base 10. And the reason why we have that is because for binary with 3 digits, this is a number as well. So that would be how we'd be representing 0. This is not 3 zeros divided by 0. I mean equivalence here. And that's why instead of just 7 numbers, or 1 to 7, we actually have 8 possibilities. The process for that will be the same regardless of the number system if we're looking at quantity. So if we look at one more binary example, what happens if I have a lot of digits? Let's look at a common unit that we see in binary is referred to as a byte, which is just a grouping of 8 digits. So how many possible numbers could we show here? So we're interested in the quantity. And we're also interested in the highest number. So we had that one approach where we could just plug in the highest numbers, but using that expansion, that's going to take a fair bit of effort to be able to work through. So there's another approach that we can use where you're applying a simple formula where you say, and let's change the color because this is a different focus again, and we will say we want to take the base raised to the quantity of digits and then minus 1. That will give us our highest number. If we just took the base and the number of digits, then that would give us our quantity. So let's look at that as an example. First we'll look at here and then we'll apply it to the higher one. Well, in this case, it's a binary system, so our base is 2. We had 3 digits. So there we had 2 to the 3. There was 8 possible numbers. The quantity of unique numbers was 8. But our highest number was, well, 8 minus 1, which is 7. And that was the largest number that we could represent. If we wanted to represent the number 8, we would have needed to add one more digit back here. But then we could represent a lot more digits. So in this example, our base is still 2, because we're in a binary system. But now we have 8 digit positions. So for the quantity, it's just going to be 2 to the 8. And before we do the calculations, let's do a small table here again. Make sure I give myself enough space. And I'm going to say the exponent for 2 and the value. 2 to the 0 is 1. We keep that as common. So we have 2 to the 2, 2 to the 3, and we keep going to get to 8. So 2 to the 1 is 2, and then we just multiply by 2 to get to the next numbers. 2, 4, 8, 16, 32, 64, 128, and then our next one is 256. Now I'm pretty familiar with these, so it might not be easy to see that, but you can always just multiply that out, just longhand. So 2 times 8 is 16, 2 times 2 is 4, plus 1 is 5, and then 2 times 1 is 2. So it's really useful to be able to build up these tables pretty quickly, or to just recognize the numbers once you get really familiar with the topic. Well, this means 2 to the 8 we look up in our table. Well, it's 256. So with 8 bits, I can represent 256 unique numbers, and our highest number is just going to be that number, our base to the number of digits, minus 1, which will give us 255. You may have seen, if you use some older systems, this number come up before. A great example of that is if you look at on the original Nintendo Entertainment System, The Legend of Zelda, the first one with the top-down view, that was the maximum number of coins that Link could have in that game. Because when they did the programming for it, they only had 1 byte or 8 bits to store the information for the coins. If they wanted him to have, say, 300 coins, then because the way the organization works in memory, they would have needed 2 bytes, which would have given us 16 bits, and then there would have been a lot of wasted space. So that's how these relate to usage as well. So you can think about it like that. And that finishes up the video for the quantity and the maximum numbers that we can express. If you have any questions or comments, take a look on the Moodle page and post them in there.